Hello all, this is Deepesh. Now, imagine a world where your computer could run programs and store data that exceed the capacity of its physical RAM. This is made possible by virtual memory. Virtual memory allows modern operating systems to efficiently manage and allocate memory resources. It creates an illusion of having more RAM than is physically available. This is achieved by swapping data between RAM and secondary storage. Virtual memory enables the execution of programs larger than the available physical memory. It enhances the system's ability to multitask. Virtual memory operates on a simple yet powerful principle: the illusion of abundance. It tricks the operating system and applications into believing they have access to a larger amount of contiguous memory than is physically present. This illusion is achieved by dividing the virtual address space into fixed-size blocks called pages, which are then mapped to physical memory frames. Pages not currently in use are stored on secondary storage, typically a hard drive or SSD, in an area called the swap space or page file. When a program needs to access data on a page not in RAM, a page fault occurs, signaling the operating system to bring the required page from secondary storage into an available frame in physical memory. By seamlessly managing this intricate dance of data movement, virtual memory provides the illusion of limitless memory, enabling modern computers to run demanding applications and handle complex tasks with remarkable efficiency. At the heart of virtual memory lies the Memory Management Unit, MMU. The MMU translates virtual addresses from the CPU into physical addresses in RAM. It performs a lookup in the page table to find the corresponding physical address. If the page isn't in RAM, a page fault occurs, and the OS loads it from secondary storage. The MMU ensures seamless virtual memory operation. While the MMU and page tables are essential for virtual memory, the process of address translation can introduce a performance overhead. Each memory access requires a lookup in the page table, which can slow down program execution. To mitigate this overhead, modern systems employ a caching mechanism known as the Translation Look-Aside Buffer, TLB. The TLB is a small, high-speed cache that stores recent address translations, operating on the principle of locality. If a hit occurs in the TLB, the MMU can quickly retrieve the corresponding physical address without having to access the slower page table in main memory. This significantly reduces the time required for address translation, improving overall system performance. The TLB plays a crucial role in optimizing virtual memory performance by caching frequently used address translations and reducing the frequency of costly page table lookups. In the realm of virtual memory, we encounter two distinct types of addresses: virtual addresses and physical addresses. Virtual addresses are the addresses that programs use to access memory, representing locations within the program's virtual address space. Each process running on the system has its own private virtual address space, creating the illusion that each process has sole access to the entire memory. Physical addresses correspond to the actual physical locations of data in RAM, used by the memory controller to access specific memory cells. When a program attempts to access a memory location using a virtual address, the MMU translates this virtual address into its corresponding physical address. This translation process ensures that each process can access its own data without interfering with other processes or the operating system. The distinction between virtual and physical addresses is a fundamental concept in virtual memory, enabling the operating system to provide a secure and isolated execution environment for each process. Page tables serve as the crucial link between the virtual addresses used by programs and the physical addresses of data in RAM. These data structures store the mapping between virtual pages and physical frames, allowing the MMU to perform address translation efficiently. Each process running on the system has its own page table, which is typically stored in RAM, and managed by the operating system. A page table can be visualized as an array, where each element represents a page table entry, PTE. The index into the array corresponds to the virtual page number, while the PTE itself contains information about the corresponding physical frame number and other relevant attributes. When the MMU receives a virtual address from the CPU, it extracts the virtual page number from the address and uses it as an index into the page table. The PTE at that index provides the MMU with the physical frame number, which is then combined with the page offset from the original virtual address to form the complete physical address. Page table entries, or PTEs, are the building blocks of page tables, each entry containing essential information about a specific virtual page. These entries provide the MMU with the necessary details to perform address translation and enforce memory protection mechanisms. The structure of a PTE varies depending on the operating system and hardware architecture, but it typically includes key components like the present bit, physical frame number, and protection bits. The present bit indicates whether the corresponding virtual page is currently present in RAM or not. The physical frame number stores the physical address of the frame in RAM where the virtual page is mapped. Protection bits define the access permissions for the page, specifying whether the page can be read from, written to, or executed. By decoding the information stored in PTEs, the MMU can efficiently translate virtual addresses to physical addresses, enforce memory protection policies, and facilitate efficient memory management. Virtual memory provides robust memory protection and access control. It isolates each process's address space and enforces access permissions. Protection bits specify read, write, or execute permissions. Violations trigger segmentation faults, enhancing system security. In a multitasking environment, where multiple processes share the same physical memory, process memory isolation is paramount. Virtual memory enables the operating system to provide each process with its own private virtual address space, preventing them from interfering with each other's data and code. When a process is created, the operating system assigns it a unique virtual address space, typically starting from address 0 and extending up to a predefined limit. Each process operates within its own virtual address space, as if it had sole access to the entire memory. The MMU, guided by the process's page table, ensures that each virtual address is translated to the correct physical address, preventing any cross-process memory access violations. Process memory isolation prevents a wide range of potential problems, such as memory errors or buffer overflows from affecting other processes. This isolation limits the scope of such errors, preventing them from cascading and causing system-wide failures. By confining each process to its own sandboxed environment, virtual memory contributes to a more secure and reliable computing experience. Virtual memory, empowered by paging, stands as a cornerstone of modern operating systems, revolutionizing memory management and enabling capabilities that were once unimaginable. By creating the illusion of limitless memory, virtual memory empowers us to run demanding applications, seamlessly switch between multiple tasks, and ensure the stability and security of our systems. Through the collaborative efforts of the MMU, TLBs, page tables, and PTEs, virtual memory seamlessly translates between the virtual addresses used by programs and the physical addresses of data in RAM. This translation process, coupled with robust memory protection and process isolation mechanisms, ensures that each program operates in its own secure and isolated environment, preventing interference and data corruption. The benefits of virtual memory extend far beyond its ability to transcend the limitations of physical RAM. It empowers operating systems to efficiently allocate and manage memory resources, allowing us to make the most of our hardware. Virtual memory is a testament to the ingenuity of computer science, enabling us to push the boundaries of what's possible with each passing day.